Hello everyone. Today we're going to start our new topic on waves and sound. So first of all, what is a wave? So when you ask people to think about the first thing that comes into their mind when they imagine a wave, most likely they will give you maybe something like this, right? Like a water surface that's moving up and down. Or they could be thinking about other waveforms, for example, like this. And sometimes we even think about waves like this one. So there are different types of waves, but what waves really are is a disturbance on a type of material that transfer energy from one point to another. Now, let me say that again. Wave is a way to transfer energy from one point to another. So now we just learned about energy in our last chapter, the chapter before. So wave is something that transfer energy. Okay, so for example, you can use a rope and you can move the rope up and down really fast, and that will transfer energy. For example, like this, like this picture, right? So you can use a rope, and you can very quickly move the rope up and down. And when you do that, what happens is you can transfer the energy that's provided from your hand to the receiver, which is on the other hand, right? So you can move something that's on the other side. So you're transferring your energy through the rope or a wire as a medium to another location. So wave is something that can do that, like water wave, for example. You can start a water wave on one end, and the water wave can travel to a different area and move stuff on the other end, right? So water wave also transfer energy from one point to another. So now in physics, we call that a disturbance. You have to move the medium at some point, and then the energy is transferred through the medium to another location. So we call that a disturbance. Now, there are two big group of waves depending on if they can go through vacuum or not. So now most wave that you can think of is actually of the second kind, which is called a mechanical wave or a physical wave. So mechanical wave are physical. That means these are the waves that you can actually touch. These are the waves that most people actually associate the word waves with. Now, so these waves cannot go through a vacuum. You will need a medium to transfer the energy from one point to another. So for example, water wave, right? So in order for someone to start a wave in water, you need water, right? You cannot start a water wave without the water. So the water is the medium. Okay? So you can start a wave by hitting the water at one point, and then the energy is going to radiate outward from your point of disturbance in the water, and it's going to travel outward and move something else in the process. So you're transferring some of your energy through the wave to another location. And we call that water wave. Now, earthquake wave is also a type of motion that can transfer energy, right? And earthquake wave transfer energy through solid rock. So rock, right? Now you might ask, Mr. Chang, how is earthquake a wave? Let me show you this picture. From previous year, I think you might have learned from previous year that from science class, right? There are two types of earthquake wave called the P wave and the S wave. Now look at this picture, which is on our course webpage. Look at the motion of the ground, right? So this is an S wave. So the ground shakes up and down. This is an earthquake, right? So the house, imagine that, you build a house on the top. So what happened is the ground shakes up and down and you feel an earthquake. Now, but there's actually another type of earthquake, which is also a wave. It's this type where the ground moves back and forth. So you see that box in the middle, that dark back box in the middle, it moves back and forth. Now, usually when there's an earthquake that happens, both type of motion happens at the same time, but then if you remember from your previous science class, the P wave travel faster than the S wave. That means the motion of the ground that moves back and forth travel faster than the motion of the ground that moves up and down. So therefore, if you're not at the epicenter, you won't experience the both wave at the same time. You'll experience the P wave first, and then the S wave comes later. That means your house will shake back and forth for a few seconds first, and then moments later, it shakes up and down. Okay, so earthquake is a wave. It's a wave that travels through the rocks. So it is a motion that transfers energy from one point to another through a medium, and that is called a wave. So earthquake is a wave. We call that earthquake wave. P wave, S wave, they're both earthquake waves. Now, you might have seen people make people wave, which is, in the arenas. Sometimes if you go to a sports event, you see people going up and down. And I have a little picture on the screen that you can see right now, just people standing up and down and making an earthquake wave, right? Well, not earthquake wave, making a people wave. People standing up and down usually are not strong enough to make earthquake waves, of course. Unless you jump up and down and there are like millions of people doing it at the same time, then maybe you can create an earthquake. So what does people wave need as a medium? People, right? You need people to make earthquake waves, to make people waves. Now, at the end, last but not least, we do have sound wave. And sound wave is actually the movement of air molecule. Now, you might say, Mr. Chang, I can see the water wave. I can see earthquake waves. I can see people waves. But I've never seen sound wave before, Mr. Chang. Are you sure that sound wave belongs to this group of physical wave that you can actually see and touch? Yes, I am sure, because sound wave is actually this kind of wave, like this, where the air molecule moves back and forth in the air from the whoever is making the sound. So we'll spend a lot more time on sound wave later on. There's a entire sections on that specifically. But imagine in this picture, the left hand side, that bar that's moving left to right on the left hand side, that is my throat. That's my when you're talking, right? If you put your hand on your throat when you're talking, you feel that vibration. So my throat is actually vibrating really fast in the air when I'm talking, and that vibration hits air molecule and make the air molecule vibrate, and the air molecule will transfer the energy of my vibrating flow to someone's ear who is on the other side, on the right hand side. For example, the receiving end is going to be your ears. So the reason why you can hear me right now is because there's a speaker that you're probably sitting next to, right? Or maybe you're using headphone. There is a speaker inside the headphone. Now, but what is really a speaker? A speaker is basically a very thin membrane that moves back and forth through the air really fast inside your headphone or your speaker. If you have a big speaker, you might actually see that membrane move sometime. Ask your parents and see if they have like a subwoofer, the big speaker that plays very strong bass. And if you play a song through that kind of speaker, you can actually see the diaphragm, the membranes on the speaker moves back and forth. So they usually go in and out, in and out. Now, of course, on your tiny little speaker that you put inside your ears, like those headphones, you won't be able to see that membrane move unless you break open your headphone, which I do not suggest that you do. But trust me saying that the reason why you can hear me is because there is a little membrane inside the speaker that moves back and forth, and it pushes the air molecule. Now, the air molecule will also move back and forth, just like the picture that you're seeing right now. Look at those black dots. Those are the air molecules. And that transfers the sound from the speaker to your eardrum. Okay, it goes inside your ear, through your ear canal, and it moves a tiny membrane that's inside your ear called the eardrum. Your eardrum moves back and forth, responding to the air that's pushing it, and your brain picks up that vibration on your eardrum and turn it into a sound. So that's why if you injure your eardrum, for example, you punch, let's say there's some accident that you have your eardrum burst, maybe like a sharp object hits it from the inside, or maybe you listen to music that are too loud, the eardrum just vibrate too violently and it bursts, then you lose your hearing for a amount of time. Sometimes your eardrum will self-heal if the injury is small, and sometimes it will not heal at all. Then you lose your hearing, basically. So without that little membrane to capture the moving of the air molecules, the waves of the sound wave going into your ear won't make any sound at all. So sound is actually a vibration in your eardrum because of the sound wave through the air. So therefore, sound wave leads air molecule. Now, technically, to be more precise, sound wave doesn't actually lead air molecule. It can be any molecules in air. It doesn't have to be air molecule. It could be oxygen gas, hydrogen gas. Sound wave can go through any gas. But you have seen it from documentary. Fish can talk to each other too, right? Whales can talk like kilometers away from each other, and dolphins can talk to each other underwaters too. That means sound wave can also travel through liquid, not just gas. Now, I want you to put your ears on the table, like against the table, and hit the table from the other end with your hand. Can you hear the sound from the table going up your ear? So if you put your ears on the table, right, and you hit the table, tap the table with your other hand, you tap it with a pencil, you can hear the sound going through the table. That means sound can also go through solid. So as long as something is vibrating, it can make sound. It doesn't matter if it's the air molecule vibrating or if it's the water molecules vibrating, like the fishes talking to each other, or it could be like a solid vibrating. Sometimes your room is completely like, so for example, if you have your own room, sometimes your brother, sister, parent playing music in the other room, and you can actually hear the music through your wall. See, the sound wave went through your wall. That is a piece of solid, isn't it? See, sound wave can also go through solid. Now, so we can put that in here. For sound wave, it has many, many mediums. It could be air molecule, gas, right? It can also travel through liquid, any kind of liquid, water or whatnot. And also any type of solid. So sound wave can actually use anything as a medium as long as that object can actually vibrate. Okay, that's why it's really difficult to soundproof a room, because sound wave can go through pretty much anything that vibrates. So the best way to soundproof a room is by building your wall with like a type of material that's so heavy that it doesn't vibrate too much. Like for example, if you have a concrete wall, is much better than like a wooden wall that most of us have at home, right? That's why on average, apartment building have a much better sound isolation compared to, let's say, like a townhouse or a house which is usually built by wood, because moving concrete is so much more energy demanding than air molecule moving wood, right? If you have a wooden wall, the air molecule just have to vibrate the wood. But if you have a concrete wall, the air molecule have to vibrate the concrete in order to get into your house, which is a, more difficult thing to do. Now, so these are just some example. I'm sure you can think of others. But remember, I said two types, right? Depending if the wave can go through vacuum, which means depending on if it leads a medium or not. Now, there are another type of waves that doesn't actually lead a medium. So these are radiations. Yep, all radiations are waves. There's actually a special name for them called electromagnetic wave. Electromagnetic radiation. Shortcut is like EM, electromagnetic radiation. This is a fancy name for light and its cousins. Light and its cousins. So they are capable of actually going through nothing, going through vacuum in space. So for example, the sun obviously is sending us a lot of energy. We can actually feel the warmth of the sun in daytime. Now that means the energy is somehow getting to us, but it's not getting to us by water wave, earthquake wave, sound wave, because there are no such thing in space. In space, sound cannot even travel. So for example, if something exploded in space, if you watch movies, right, they show you exploding sound. That's actually ridiculous. In space, if let's say a bomb went off next to, and you're seeing a bomb, going off next to you, you should not be able to actually hear the explosion, because where's the air? You need air, liquid or solid, to transmit the sound wave to your ears. So where's the solid air, liquid, and solid in space? Nothing, right? So that doesn't exist. So electromagnetic radiation. So any type of radiation, for example, radio wave, infrared radiations, If you have a heat lamp, let's say you go to a buffet, sometimes you see in order to warm up the food while it's waiting for to be eaten, they have like this heat lamp installed on top. It looks like a red colored lamp, like a light that's red in color, and it keeps the food really, really hot. So that is sending out infrared radiation. Microwave, the one that's in your microwave oven, or your cell phone actually use microwave to Wi-Fi is microwave. Your cell phone is using microwave to communicate with the towers. Your microwave oven uses microwave to heat up water. Bluetooth is microwave, by the way. Almost all the communication radiations are microwave. So these, for example, when you're so if you look at your Wi-Fi routers at home, what is it doing? It's broadcasting microwave radiation, which is a form of energy, so that when your computer receives that energy, it's collected to the internet, right? So the information is sent from the tower that emits the Wi-Fi. You can find one in your house, I'm sure, and your computer is the receiving end of that energy. See, transfer of energy, which is a wave, right? A wave is something that transfers energy from one point to another. Light, visible lights, the light that you can see when you turn on the light, that is also a wave. You just cannot touch it, but it's a electromagnetic radiation. Ultraviolet, UV, ultraviolet radiation, usually that's from the sun. That's why you have to wear sunscreen, because that will give you skin cancer if you are not careful. X-ray is not a wave that you would deal with from day to day, but if you have a broken bone, the X-ray can actually penetrate your flesh and look at the damage in your bones. That's why when you go to the doctors, they might give you an X-ray scan if you have a bone injury. Or if you go to the dentist and they have to X-ray your mouth to see the bone structure of your teeth, in order to come up with better treatment, they will usually ask you to wear an apron, a lead apron, because they don't want the rest of your body to expose to X-ray. I mean, they have to see your bone, so yeah, your mouth has to experience that X-ray scan, but they don't want your head to do that. They don't want your eyeball to actually get hit by the X-ray. They don't want the rest of your body to get hit by X-ray. So they give you this really heavy apron, right? I want you to think about the last time you go to your dentist. That apron is made with it's actually made with lead, right? Lead, one of the element Pb. Lead can actually block most radiation. Now, but of course, it's also poisonous. That's why you're not going to, please don't eat that apron. You can wear it for a little while. That's okay, right? But it blocks the radiation, so your body doesn't get the unnecessary harm. Except for the area that the doctor wants to see the bones with, right? Gamma radiation, that's from nuclear bomb, from nuclear waste, from power plant, cause mutation, cause cancer, kills a lot of people, right? If it's not used properly. When it's used properly, it can actually be quite useful. So for example, gamma radiation, which is a very, very strong electromagnetic wave, can actually kill off most bacteria. That's why if you go and buy a box of strawberry from a supermarket, instead of going to the farm to buy it, right? If you buy a box of strawberry that's already picked for you, that box of strawberry, before they put it on the shelf, they actually use a gamma radiation gun or light to kill off all the bacteria so that it can last for longer during transportation and on the shelf. Yeah, so that box of strawberry that you're eating, a lot of fruits too, not just strawberry, has been exposed to gamma radiation to kill off bacteria, right? Because the gamma radiations are so strong that it can kill off a lot of things, so bacteria being one of them. Now, let's pick up the next part. So now there are mechanical waves and radiation waves or electromagnetic radiation. Mechanical waves leads a medium to travel, whereas radiation, electromagnetic waves, does not need a medium. It can actually go through vacuum. Okay, now, so for Physics 11, we're going to focus on the mechanical waves, and mechanical waves have two main distinct type of traveling. I think you have seen it the picture that we saw earlier shows you those two types. So one is called transverse, and the other one is called longitudinal. So longitude, then no. So transverse versus longitudinal. These two are just the way that the wave moves, the mechanical wave moves. A mechanical wave either moves kind of like up and down or back and forth, depending on how the mediums oscillate. So we'll look at those pictures again. I'll tell you which type is which. So the difference is how the medium, like the air molecule or the water molecule, how do they oscillate? Do they move up and down or do they move back and forth? Okay, now let's look at the first type, which is the transverse wave. Now, these are the type that commonly most people, when you ask them what does a wave look like, they think about this one. This is a transverse wave on the screen right now, ladies and gentlemen. Now, what is so special about it is that the wave, so the molecule, now this is a rope, right? But you can also think of it as, it could be a water molecule, it could be other thing that's moving up and down. Now, if you look at the red dot is like an individual air molecule or individual part of the medium. But if you look at the red dot is actually just moving up and down, right? Now, if you look at any molecule, any particles in the medium, none of them is actually going from the left to the right. None of them are. They're just going up and down, and then the shape of the wave is going from left to right. So you can see like a wave traveling from the left to the right now, right? But no particle is actually going to the right. Like no particle is actually physically, like you cannot say one of those molecules is physically going from the left to the right. Like look at any molecule, any one of them. They are just going up and down, up and down, up and down. Just like when you have a people wave, the people doesn't have to go anywhere. The wave looks like it's going somewhere. Like, so 1 second. Let me show you a people wave again. So look at this people wave. Look at the people. The people are just standing up and down. No one is actually going to the left or right. But the shape of the wave, the energy is traveling to the right-hand side in this case, right? So that is the definition of a transverse wave. In a transverse wave, okay, so let's put it down in here. All right, so in a transverse wave, the particles moves what? Perpendicular, okay, to the direction that the wave travels in. So the particle moves perpendicular to the direction that the wave travels in. So the wave goes, for example, from in the picture that you saw earlier, from left to right, but the particle are only moving up and down. So for example, a wave moving along a rope or a string is a good example of a transverse wave. So you look at the wave motion of the wave, let's say it goes from the left to the right in this case, right? But if you look at an individual particle, what they're doing is they're just going oscillating up and down. Okay. So for example, if I ask you to predict the motion of this red particle a moment from now, well, you have to say that it goes down, right? I mean, it is already at the highest point. Where else can it go, right? So, or if I ask you to predict the motion of this red dot right here, then you have to say that it goes up because, it's already at the lowest point. Where can it go? So the particle moves up and down, but the energy goes from left to right, okay? So the wave of the motion of the wave is also the direction of the energy transfer. Okay, so the energy transfer. Okay, also go from left to right in this case. Now, what about, okay, so which one of these examples are longitudinal, are transverse wave? So for example, people wave, definitely. If you make waves in a rope or string, like you just move your hand up and down with a rope, that is definitely a transverse wave. What else? Water wave is actually could be both. And earthquake could be both too, because if you look at the earthquake picture from the coursework page, earthquake right here, right? This earthquake wave. The S wave is actually going up and down. So you can see the direction is going from left to right, right? This earthquake wave. But look at the box. Look at that black box in the middle. Look at which direction it actually moves as the wave goes through it. It doesn't actually go up left to right. It just go up and down and then back to the middle, and that's it. But the wave travels from left to the right. So the particle motion is perpendicular to the motion of the energy, and that is a transverse wave. So you can say that S wave is a transverse wave from earthquake, whereas the P wave is something else. Okay, so that's another example. So if I ask you to give me examples on transverse wave on the test, or for example multiple choice question usually, then that's another example you can give. Okay, so now the second type of movement of mechanical wave is called longitudinal wave. Longitudinal wave, which is also called a pressure wave because you have to apply pressure, or a compression wave because it looks like something is being compressed. It's harder to visualize this, but it's actually more common because one of the most commonly, senses that we use is sound wave. So sound waves are longitudinal wave. Okay, so in this type of wave, which I'm going to show you on the course webpage, of course, you have the particles right here, right? So you look at this wave right here. You can clearly see that the wave is moving from the left to the right hand side. But if you look at an individual molecule, look at those red molecule, any one of them, all they are doing is oscillating left to right. Now, but still, not a single molecule is actually going all the way from the left to the very end at the right hand side. They're not actually physically moving. They're just vibrating, not vibrating. Well, yeah, I guess they are oscillating back and forth, and the energy is going to the right hand side. Okay, so then this is a longitudinal wave. Okay, so sound wave is one of them. If you have a slinky, if you have a slinky and you make a wave with a slinky, that will also be this type too. So in this picture, there's a slinky, right? So if you have a slinky, it could also make this. All right, so now in a longitudinal wave, the particles moves in the same direction. Okay, so they move in the same direction as the motion of the wave. So the particle moves in the same direction as the motion of the wave. So that's how you can tell the difference between the two. Now, for earthquake, the P wave of an earthquake is a longitudinal wave. So earthquake has both longitudinal wave and transverse wave, depending on if you're talking about the P wave or the S wave. Okay, so if you look at this one, the ground is moving back and forth, so every molecule inside is moving back and forth too, which in this case is moving from left to right because that's the direction of the energy propagation also. All right, so moving on. So a lot of definition. Now, there are other types of mechanical wave. For example, water wave is usually a mixture of the two. So water wave is usually a combination, okay, of both type, of the transverse wave and the longitudinal wave. So the water molecule move up and down and left to right at the same time. So they create something that looks like a, so if you look at like a wave, like a water wave, and you look at one of the water molecule, you will find that what they're doing is actually going in a circle. So they're going up and down, but also left to right at the same time. So they're going like kind of circular. So what if you look at like an individual water molecule, that's what they look like. So we will say water wave is both longitudinal and transverse. Okay. Now, I think this, okay, so now there you go. All right. Now, how can you generate a wave? Usually there are two type of wave that people would like to generate. Either the first one is a pulse, which is just generating one wave by moving the material very, very quickly in the air. So let's use transverse wave or longitudinal wave. Let's say if you want to generate a pulse, right? You can do that by rapidly deflecting the medium or compressing the medium. So if you want to make a transverse wave, you would deflect the medium by moving up and down. If you want to make a pulse of a longitudinal wave, you compress the medium really fast and then returning it to normal. The result is a single wave that moves forward in the medium, which is going to be like this picture. So let me show you a picture of that. See? So it's like a pulse, right? So now, of course, string pulse. There you go. That's another one. So imagine that, yeah, someone just moved that string really fast up and down, then you get a pulse, right? So this is a transverse wave, by the way. I don't have a picture for a longitudinal wave animation for that one, but it will actually be this, like, so someone compressing this linky really quickly at the beginning. So that will be a longitudinal pulse. So that's a pulse, right? Okay. Now, so for example, if you make one, so at the beginning, so you deflect the you deflect the medium, and then let's say you just go up and then back to normal. Then a few moments later, that wave is going to arrive somewhere over here, maybe in the middle, like this. Oh, just 1 second. Oops. Okay, there we go. We're back. Okay, so it will go like up and down, like that, and then later on it will travel. So let's say the direction of the energy traveling is to the right hand side, then eventually that wave is going to go to the right hand side too, right? So you make it once, and then it will travel to the point until it loses all of its energy. Now, one thing you do have to notice is the width, right, of this pulse should remain the same throughout the process. So it doesn't suddenly get longer or shorter. Okay, so the length of that pulse should be the same throughout the process. Actually, the length of a wave is called a wavelength. We'll learn that. We'll actually talk about that more in detail next time. Now, what if you go up and down and then back to normal? Then you create something that has both an amplitude on the top and amplitude below, and that will also travel. Obviously, that will also be able to travel up and down, and then at the end, like that. So it will be able to move from one point to another. So this is again now if you look at the length again, right? The length should be exactly the same throughout the process. So the wave of the length of the wave doesn't change as it's traveling along. Okay, now that is sending a pulse. But sometime, what if you want to send a wave that has more than one source? I mean, a wave that has more than one pulse. What if you want to send a periodic wave? That means a continuous wave. Now, you can actually do that. And what happened is you just keep moving that system up and down, keep disturbing the material repeatedly. Okay, so you just keep disturbing it over and over and over and over again, and you will get a repeated wave like this. So you make one and then you come back down, and you make another one, you come back down, you make another one, you come back down. So eventually it will look something like this. And as long as you don't let go, you keep making it, then you will get a continuous string of these wave pulses, and these are called periodic wave. That means you're making them periodically, and they follow some kind of a structure. So what will be like some examples of the first type or the second type? Well, think about it this way. So what is a pulse? If you make like one sound, right? Let's say you make one sound. So you go like boop, and then that will be a pulse. So what will look like the periodic wave if you make a sound that lasts for a long time? For example, you go like ooh. If you have a machine that can actually record what I just did, you'll see a periodic sound wave that goes up and down, 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 up and down. Whereas if I did oh or ooh, that would be a pulse. And if I did ooh, that would be periodic. Because in order to maintain that sound, my throat actually has to move back and forth continuously. Whereas if I just want to make like one sound, I only have to move my throat one time. So that's a pulse versus like a periodic wave then, right? Okay, so now pretty short, all definition. Basically, I don't even have to, well, there's no worksheet, I think, associated with this one because really, you just need to remember the information. I mean, yeah. So all these informations are going to be, you will need to memorize them. I think except because we are not paying too much attention to the electromagnetic radiation, so you don't need to know, memorize every single one, but you should know that they exist. You should know that there are two types of waves. One type that is physical, that you have to have a medium in order to for them to travel and transfer energy, and one type can actually go through a vacuum, which is the electromagnetic radiations. Yeah, electromagnetic wave or electromagnetic radiations, same thing. And you should know approximately what they include. All right, and be ready to give examples. For example, give some example for longitudinal wave, give some example for transverse wave, and so on. Okay, so it's more definition and know how they travel, perpendicular or parallel, right? Okay, so goodbye, everyone, and that's it for this session.